Okay, guys. Oops, here we go. Sorry about that. We are going to discuss free energy change as basically we're going to be looking at Gibbs equation. What does it mean and why the heck do we do it? So biologists want to know which reactions can occur spontaneously, which means can that reaction occur without the input of energy? So to do this, we need to determine the energy changes that occur in this chemical reaction. So a living system's free energy is the energy that is available to do work. Okay? It is what we like to think of as not necessarily free energy, but it is the available energy for the cell. So if you didn't see that word right there, is available. So what is Gibbs equation exactly? Gibbs equation says that the change in free energy, or delta G, during a process is related to the change in enthalpy, which is our change in total energy, delta H, and a change in entropy. And remember, entropy is this change in disorder. So delta S is change in disorder, and then T is our temperature. Now, only processes with a negative delta G are spontaneous. How do you get to be a negative delta G? When the final delta G is less than the the initial delta G. So let's go over that again. What we see here is when the final amount of free energy is less than the initial amount of free energy. That's how we're going to get a negative delta G. And so we take these spontaneous processes, our cells take them, and we can harness that energy to perform work. So free energy, stability, equilibrium. How does this all go together? Well, free energy or available energy is a measure of a system's instability. The more stable a system is, the less available energy it has. The more unstable a system is, the more available energy it is going to have. So during a spontaneous change, free energy is going to decrease and the stability of a system increases. And we're going to look further at this in class by drawing some graphs. Now, equilibrium is a state of maximum stability. This is what I want you to understand, right, from theoretically speaking from this. If I have a molecule and I break it down, I am taking it from a place of potential energy and I am converting it to kinetic energy, and that energy is being released from that molecule, right? So what we're seeing happen is the available energy is less in the product than it was what we started with because energy was released. That is spontaneous. At equilibrium, we're at low free energy, guys. There's nothing there. It's stable. It doesn't want to change. It doesn't want to go through any spontaneous reaction. Why would it? It's at equilibrium, right? So we have low free energy at equilibrium. And so a process can only be spontaneous if it is performing work while it is moving towards equilibrium. So let's take a look at this. With gravitational motion, we've talked about potential energy versus kinetic energy. And we know this guy up here has potential energy. What does that mean? He has a lot of available energy. Okay, but he's not real stable. He's busting out to get rid of it. And he jumps, and we know that when he jumps, that gravitational motion is going to convert that potential energy into kinetic energy. And what's going to happen is we're now going to have less available energy because once he hits the water, we don't have as much energy, but more stable. Okay, so let's take a look at diffusion. Diffusion here, we have a cluster. We have a lot of available energy. They want to move. They want to become more stable. A lot of available energy. They want to become. So sorry, I can hear my children bouncing upstairs. They want to become more stable. So we're going to move from an area of high energy to an area where there is less available energy, okay, and they're now in a more stable area. Now this is probably my favorite example over here, and here's why. Because we are going to be talking about cellular respiration, and cellular respiration is a breakdown of glucose. So if this molecule right here is glucose, we're looking at a molecule that has a ton of potential energy, which means that it has a lot of available energy, and it's unstable. Okay, not much stability here. It's going to be broken down into smaller, simpler components that have less available energy, okay, but is more stable, right? So the concept of free energy can be applied to the chemistry of life's processes, i.e. we're going to apply this to cellular respiration. Big terms that we need to know here. Exergonic. Oh, let me get my pen. Exergonic reaction proceeds with a net release of free energy and is spontaneous. An endergonic reaction is what absorbs free energy from its surroundings and is non-spontaneous. You can easily apply these to two other terms that we have learned before. Exergonic is a catabolic reaction, and I really struggle with this, so I'm just going to write cat. And an endergonic is an anabolic reaction because it absorbs free energy. Whoa. Anna. Okay. So let's take a look at our graph on this one. I like this graph because it simply shows in an exergonic reaction that energy is going to be released. On our x-axis here is the progress of the reaction. Here are my reactants. They have a lot of free energy. So they're going to spontaneously go through this where they are broken down into their products, and their products have less free energy than what they started with. Therefore, delta G is going to be negative because, again, you take your final amount of available energy, subtract it from the, you take your final amount of available energy, subtract the starting amount of free energy, and therefore you get a negative number. Now, in an endergonic reaction, we see the opposite. Our reactants have less available free energy, and we're going to combine those reactants to make a product that therefore is going to have more available free energy. Therefore, delta G is going to be greater than 0. We're going to have a positive number, and we have an endergonic reaction. So equilibrium and metabolism. Reactions in a closed system eventually reach in equilibrium and then don't work anymore. Cells are not in equilibrium. They are open systems experiencing a constant flow of materials. Think about our human body. We are constantly receiving oxygen from our blood, glucose from our blood that was absorbed through the small intestines. So a catabolic pathway, remember, is going to be exergonic. In a cell, releases free energy in a series of reactions. So to do a quick analogy of this, check out these closed and open hydroelectric systems. In a closed hydroelectric system, we see the water level here. We know the high water level, that's going to move down. And when that water moves down, it's going to release energy that causes work to be done. And that turbine's going to move, right? Eventually, though, this system is going to reach equilibrium and no more work can be done. Delta G is now equal to 0 and the work stops. It's at equilibrium. It's stable. In an open hydroelectric system, we have a constant input of water. When that occurs, this level never goes down. Therefore, the water continues to flow downwards, releasing that energy to cause work. There we go, right? And it never hits equilibrium, and therefore delta G is less than 0 or negative. So how is this related to us? Well, cellular respiration is like a multi-step hydroelectric system. where in cellular respiration, we see, again, the constant input, which is that constant input of glucose, right? Glucose is coming into our cells. We're powering it. It is then releasing energy to do work, that spontaneous reaction. The products of this reaction then become the reactants of the next reaction, and it goes on and on and on. So delta G is always less than 0, and it's always moving towards equilibrium. So cellular respiration is very unique in the sense that it is moving towards equilibrium. It's never going to hit equilibrium because we have this constant input of glucose, or that energy that we need. Huge. That's awesome. Because if it didn't, if it stopped, we stop giving glucose. Now it's closed. No more glucose is coming in, just like no water. Then that cell is going to hit equilibrium. And if that cell hits equilibrium, there is no more available energy to do work. What's going to happen to that cell? It's going to die. So it's important that we keep that open system, that constant influx. Okay, now, so coupled reactions. So in the cell, the energy from the exergonic reaction of ATP hydrolysis is going to be used to drive an endergonic reaction. So ATP hydrolysis, which is in your next flip, is going to be the splitting of that ATP molecule. Give me 1 second. The splitting of that ATP molecule in order to push forward the endergonic reaction. Okay, so we're going to take the energy that's being released from this reaction, and we are going to use that to push the other reaction forward, that endergonic. So overall, the coupled reactions are going to be exergonic. Let's take a look at this very quickly. I have to go pick up my other child. So we have glutamic acid plus ammonia. This is an endergonic reaction. How do we know? Well, anytime we're combining two simpler molecules to form a larger, more complex molecule, that's endergonic. Energy is being absorbed here. So we have 3.4 kcals. It's positive, so we know it's endergonic. So in order for this reaction to occur, it must be pushed forward by an exergonic reaction. What's our exergonic reaction going to be? It is going to be the breakdown of ATP. So when ATP goes through its reaction, the energy that is released powers the glutamic acid forward by phosphorylating it and then allowing this reaction to occur. Now, we're going to look exactly at, well, how the heck does ATP do this in the next flip? But what I want you to see here is that the delta G that is required to make this reaction happen is only 3.4. And the delta G that we get from the hydrolysis of ATP is negative 7.3. So the end result, delta G, negative 3.9. It's still an exergonic reaction because the amount of energy needed to push the reaction forward is less than the amount of energy that was released from ATP hydrolysis. Okay, we're going to get a lot of practice with this. We're going to make this applicable, and we're going to push it towards cellular respiration so you can actually see this in motion. All right, and that's all, guys. We're done. See ya.